Hi there everyone, welcome to this next video. We're going to be talking about here parametric and non-parametric tests, hypothesis tests. Okay, as mentioned on the previous video, when we spoke hypothesis testing, right, that was the topic of the last video. Now it's a continuation of that. And remind you that the next video is linear regression, right? So linear regression is going to use some of the points we discussed about hypothesis, okay? So let's see, okay? A little bit before we go to the slides. So again, we're going to see, because I did a comprehensive, or more or less comprehensive explanation of parametric, non-parametric testing on the previous video, right? Here, we're going to go straight to the point here. I'm going to show you two examples of non-parametric testing and how to do tests that's not on the parametric way, because that's what was missing on the previous video, okay? So I'm going to go show again one test of correlation, a test of independence, right? Showing non-parametric ways to do that. And so hopefully you can get that idea. Now, my considerations here, my comments. Do you need to remember how to do those two non-parametric tests I'm going to show here to you? At least know how to describe the main points of it. I don't know if you're going to have to perform one of those tests in the exam, but definitely those names might appear there, right? So you're going to have to at least be comfortable with that, right? For example, we have one test called Spearman rank correlation coefficient. Spearman test of correlation. It's a non-parametric test for correlation. So I don't know if you're going to have to remember the name Spearman test, okay? I don't think you're going to have to remember all the steps of the test. I'm going to show you here to you. But we never know. Maybe a conceptual question about it, then I think you might face. Okay? All right, so let's see. It's not a long module, right? You're going to see there's not many learning outcomes, so you should be fine here. So let's see. Let's see the slides. There you go. You see, we have here about three. It's divided in two, but actually kind of three main learning outcomes. Voila. The first one, explain the parametric and non-parametric test of hypothesis for that the population correlation equals to 0. Okay, so look at that. The learning outcome here, friend, is emphasizing, okay, a non-parametric, well, parametric we already explained it to you, the test of parametric, a test of correlation, we already did it, but here it's emphasizing a non-parametric test of correlation, which I'm going to show it to you, okay? Determine whether the hypothesis is rejected at a certain level of significance, okay? And that would be my second point here. So the first one will be explain the test, the second one will be determine this if you're going to reject or not, and the third one here, which is number 2, explain the test based on contingent table, which I have an example here to show it to you. Okay, a contingent table showing a test of independence that's going to be on non-parametric. Okay, but that's it. All right, let's see the key points. All right, so test concerning correlation, parametric test of correlation, non-parametric test of correlation, or the Spearman rank coefficient or correlation, in the test of independence using the table. That's it. Those are the 4 key points that we have there. Here you see 5, but unfortunately there's a typo here again on the word coefficient. Should be part of the learning outcome C. So in reality you have 4 learning outcomes here. Test, correlation, parametric, non-parametric, and the contingent tables. Okay? All right, let's go to the Excel, not Excel, but this one here is my notes, which I usually do on Excel. But that's the notes that I have for this slide, for this topic. Look at that. Parametric and non-parametric test. Okay? We already mentioned here the learning outcomes. Okay? We already mentioned the key points. Okay? So let's go straight to the point. This one here, I'm going to go quick because I already showed this example to you. I just brought it back to kind of like, emphasize one more time that this is the parametric test for correlation. Look at that little formula again. This r square root n minus 2 divided by square root of 1 minus r squared. That's the parametric test. All right? And you're going to reject if your value is higher than the predetermined, the whole deal. Now, let's talk about non-parametric test of correlation, called the Spearman, okay, rank correlation coefficient, okay? So try to remember this name, okay? And let's see here how it goes. So the Spearman rank correlation coefficient is a measure of strength and direction of a relationship of two variables. That's correlation, right? They move together to the right. They move together to the left, right? They move together in the same direction. They move together in the opposite direction. That's what it is. Like stock price, for example, right? If axis whether the rank of the values of two variables move together or not. So now imagine that you're going to do a test to see if two variables move together and which intensity they would move together. If it's from -1 to +1, exactly as normal correlation goes from -1 to +1, this test, the Spearman rank correlation coefficient test, will address that. Will give you a number that's closer to -1 or closer to 1, okay? Or excuse me, it's going to give you a number that's between -1 and 1, whatever number it is. That's the answer, okay? All right, so let's see here. The correlation coefficient is computed by applying the following formula. Right. Do you need to remember this formula here? I hope not, but I don't know. I don't know. All right. So I'm protecting all the angles and I put the formula here for you. Look at that. So the correlation coefficient, the whole, right, equals 1 minus something. What is something? 6 times the summation of d squared. What is d squared? D squared is the deviation square, variance. So look at that. 6 times the variance divided by n times n squared minus 1. So look, if you can break down this formula in a way like this, look, it's 6 times the variance divided by n, but this n will be multiplied by n squared minus 1, just to kind of like increase the denominator a little bit. Right? So the denominator here, it's not divided by n. It's divided by n times n squared minus 1. But in reality, it's a numerator. What you have here, right? If you can observe, like you have 1 minus, then a numerator divided by a denominator, right? Here I put that sum of the d squared represents the sum of the square rank differences. Okay, differences, deviations, differences, n is the observation. So really, if this was an exam question, they probably would give you the d squared, they give you n, and you probably have to remember that you have to multiply by 6, divided by n squared minus 1, and then 1 minus that number. Okay, anyway, I'm going to show you an example. Okay, so just giving you some more clues about it. The Spearman correlation coefficient ranges from -1 to +1. Okay, -1 perfect negative correlation, +1 perfectly positive correlation. 0 is called monotonic relationship, just in case, right, those words appear there. So the word monotonic, okay, negative monotonic, positive monotonic, it's a typical word related to the non-parametric test for correlation. Okay, all right. The Spearman rank correlation coefficient may be used to find correlation of several assets, not only 2 at a time. So this could be a question, right? Which of the following most likely incorrect? The Spearman rank correlation, one of the limitations of the Spearman correlation coefficient method is that's only applicable to 2 variables at a time. Wrong, right? You can use for several assets. So again, try to get on the definitions, right? What questions they could ask you about related to it. Good. Yeah, so let me show an example. Let's see an example here of the Spearman rank correlation. There you go. Look at that. I create that for you. See, you're going to notice that it's very time consuming. Right? Of course, it depends on the number of observations, but you're going to get at least 5, 3, right? 2 observations doesn't make any sense. So I believe that the test itself, you're not going to need it to do it. But I want to show you how to do it, so at least you understand the steps, might help you to answer questions related to it. All right, so look at that. Remember, another thing is the keyword for non-parametric testing is ranking, ranks. So look at that. Take company A, company B, okay? And I'll take here a month. So look at that. I have the returns of company A, 3, 2, 4, 1, 5, 3, and 6. Company B, those are the returns. Now, what do? I'm gonna rank each company's return from lower to higher. So look at that. Number 1 is assigned to 1% for company A, because that's the lowest return in the list. Equal returns, you put equal rankings, okay? Now, the second one here, 2%, 3%, okay? 3% again, look at that, see? You got number 3 here, okay? So you don't have number 4, okay? You don't have number 4, okay? Because the second 3% occupy the 4th place, okay? So there you go. Then you rank according to that, take all the ranks assigned for each return. Do the same for company B. Now, pay attention, compare them, keep the months, look at the months. January, February, March, April. But now I'm gonna do the difference in ranking or returns according to the month. So during January, look at that. The difference in return was -3. Company A gave me 3%. Company B gave me 6%, the stock, right? So there's a difference of 3%, which when I square, I get 9. Same deal here, look, March. March, the return of company A ranks in 5th place. The return of company B ranks on 4th place. 5 minus 4 is 1, 1 square is 1. Last one, just to emphasize the example. In July, the company A return of July was number 7 in the ranking. In company B, it was number 6 in the ranking. The difference in rankings is 1, 1 square is 1. Great. Now, I add all those differences. That's my sum of d squared that you saw in that previous formula. Remember, the sum of d squared, okay? So, go back there. This guy here, remember, the sum of d squared. That's my last column that you saw in this example. I got 15. Now I can replace that on that formula. 6 times 15 divided by n times n squared minus 1. So look at that. 6 times 15 divided by 7, which is n, times 49, 7 squared, minus 1. Answer, 0.7321. It's a positive, strong correlation between those two returns, company A and B. Okay? Very, very interesting way to do it. You see it? And you arrive on an answer. We got a conclusion here, right? We're able to kind of, well, you know what? The returns of company A and B seems to be correlated on the degree of 0.73%. Okay? The monotonic positive relationship of stock A and stock B is 0.73. Okay? That's it. That's the Spearman non-parametric test of correlation. So the key element is, remember that formula, 6 summation of the variation divided by n multiplied by n squared minus 1. Okay? Again, I don't know if you need to, if it's going to be a question like that, that you have to do it, those steps in the exam. I found impractical to ask you a question like that. I found easier to ask questions related to the definitions. All right. Now, let's see the next point to explain, the next key point, which was the tests, there you go, of independence using a contingency table. So what is a contingency table? That's an example of a contingency table. You have choices, right? And you have, in this case here, sentiments, views about each one of those investments. And that's a typical test of independence, okay? So there you go, test of independence using contingency table. I want to know if the positive, neutral, and negative sentiments are independent, right? or if there's some kind of dependence of how the person feels, right? For one, if it's based on the other, or if it's just like different independent sentiments. That's the idea. All right. So the purpose of the test is to access whether the observed frequency of a contingent table is significantly deviate from what is expected. Okay? Under the assumption of independence of variables. So it's a test of independence. The key word here is test of non-parametric test of independence. Okay? How do I do a parametric test of independence? Well, I'm going to do a parametric test of parametric is the difference on the means of the observations, and then I do a t-test on that, right, using the t-distribution. I don't have that here. This is non-parametric. I'm going to use a ranking way to do that. Okay, so look at that. Actually, no. For the contingent table, in this case here, let me see if it's a non-parametric. I believe it. Oh, no. This one here, friends, excuse me, it's a parametric test of independence, not the non-parametric. I'm not there yet. So I'm explaining now the parametric test of independence using the chi-square distribution. Now, I am almost convinced that if you're going to have to perform something related to the chi-square test, it will be given on the problem that you should use the chi-square test. Okay? All right. So because the most commonly used test for independence with contingent table is the chi-square. The mostly common, I even should say here, the most commonly used parametric test, even going to call parametric, just to emphasize that, test for independence with contingent table is the chi-square. Why is parametric? Well, chi-square is a distribution. So if I'm using distribution, I'm using a parametric test. Chi-square test calculates the chi-square statistics by comparing the observed with the expected and divided by the expected. That's going to give you a number. You're going to compare with a critical value, then you're going to reject or fail to reject the independence or lack of independence, depending on what you're testing here. Let's see an example. That's simple. Suppose you want to explore where the relationship between investor sentiment and the investment. So you have stock, bonds, commodities, and you have a positive, neutral, negative sentiment associated to each one of those three. We're going to test the independence of that using a chi-square test. Let's see how this is done. So this is not the ranking test, okay? Because this is parametric. So for parametric, I just need to do as given, okay? So look at that. State the hypothesis. New hypothesis. Investor sentiment, investment preference are independent. So means association equals 0. Okay? Alternate hypothesis. Investor sentiment, investment preference are not independent. So there you go. Okay? All right. I might reject that they are independent or fail to reject that they are independent. Significance level because, again, we are on a parametric test. Calculate the expected frequency. Under the assumption of independence, calculate the expected frequency of each cell, okay, which is those numbers here. All right. Calculate the chi-square stats. So there you go. That's the formula. Summation of observed value minus expected value squared divided by expected value. Okay, you add all of them, okay, and then you're going to determine if you're going to reject or not based on your calculation. Okay, so that's your test, the chi-square stats. The terms of the degrees of freedom, because see, I need a critical value, correct? I need a critical value. If I need a critical value, I need confidence level and degrees of freedom. If I'm using any parametric test, I'm going to need confidence level and degrees of freedom. Therefore, this will give me the ways to go to a table and get the answer I want. So what we're saying here to you, and if you want to memorize that, I would recommend, is that the degrees of freedom calculation for a chi-square test of independence is done as row minus 1 times column minus 1. Okay? Number of elements in the rows. You see the column has three elements here. Okay? And the rows have 3 elements. Okay? So then you have to do it. They are minus 1 times R minus C, C minus 1, that gives degrees of freedom. You have the degrees of freedom, okay, takes the degrees of freedom with your 95% significance level, and you can get a critical value for your test, okay? So again, I'm describing here to you, but how much this will be in the exam, or is this intensity, I'm not able to tell you, but I think it's unlikely, okay? For a quick, because you have 90 questions in 2 hours and 15 minutes, so you don't want to have longer questions, too long, not going to be in the exam because of that. If you find a question that's long, and you know that's going to take time to answer, that's because there were many questions before or after that's going to take you a few seconds to answer. So you have on average an hour, 1 minute and a half to answer each question. If you take 30 seconds in one question, you have an extra minute for the other question. So every now and then you're going to get a longer question, but those are not going to be the majority in that exam. The majority is going to be fair questions based on the material that if you prepare, you're going to have short, you don't need much time to answer. All right, and then you make a decision. If the test statistic exceeds the critical value, okay, and the significance level rejected no hypothesis. I want to make a comment here. Is a prerequisite. I should have said that on the hypothesis test, but I didn't, but it's a prerequisite. Is related to the p-value. What is the p-value? Okay, I'm gonna explain more, I promise, on linear regression. Linear regression, the p-value is gonna be super important. So for now, I'm just gonna show it to you using the graph that I showed on the previous video, this one here, okay? The p-value is this number outside the curve, the percentage outside the curve. Notice that I have a percentage outside on the right side here of 2.5%. And on the other as well. 2.5 plus 2.5 is 5%. That's what we call a 95% significance level two-tail test. Because I have two tails here. Okay? I have two tails. If it was a 95% one-tail test, my p-value would be 5%. And it would be only on this side here or on this side here if it's higher or lower. Okay? I will explain more about the p-value on linear regression, but the p-value means if it's very small, that means you're going to reject any hypothesis. If p-value calculated it's smaller than 2.5 or 5% if it's one tail, you reject any hypothesis for a tiny p-value. On linear regression, we're going to show this in more examples. All right, let's conclude this. Now, another non-parametric test, okay? That's non-parametric test, okay? This non-parametric test is called the Wilcoxon rank. It's a rank. So again, the word ranking must be associated to non-parametric test. That's the way of doing non-parametric test is ranking, right? And using the ranks and some definitions, we can arrive on the conclusion here, on the decision that we try to make. So let's see an example here, okay? A financial analyst is interested in comparing the performance of two investment strategy, A and B, and there's the monthly returns right there. So look at that. A, 2%, 1%, all this set, and B, there you go. Now, look what this, and I predict if the question is in the exam, they will tell you to use the Wilcoxon rank test. If you get, they're going to ask you to use the Spearman correlation test. Okay, so they're going to give you the name. Now, they might ask a question where the alternative will be one of those names. Wilcoxon, Spearman, and chi-square. Which of the following tests, non-parametric tests you use for test of correlation? A, Spearman, which is the answer. B, Wilcoxon, no. C, chi-square, no. Okay, so think about that. How could an easy question would show up related to this? Okay, don't think like how a very super complex difficult question would. No. All right, so look what you do. State the hypothesis. A0, there's no difference. I want to refute that, or I want to fail to refuse, fail to reject that there is no difference, and therefore I might conclude that there is a difference in performance. Well, that's my hypothesis. See, the hypothesis here is stated in English language, let's say, right? There's no higher or equal here, huh? Is that there is no difference. There is a difference. So you kind of stated, writing, okay? Nevertheless, it's a hypothesis. Right. Now, let's do the difference on those strategies. So I do 2 minus 0, okay? 2 minus 0, I get 2%. Then I do 1 minus minus 1, I get 2% again. Then I do 3% minus 1%. See, I'm doing the difference of strategy A and strategy B returns one by one. So I put that in order, right? And then I do one by one, okay? The order, I mean, that month, exactly as I did in the previous. Remember, January, February, March, here going to be the same. They have to happen on the same month so I can compare. So I'm taking the difference now. So look at that. I create a sample, right, only with the difference in performance. Because that's what I'm testing. Look at my hypothesis. The hypothesis, there's no difference in performance. Well, logically, if I want to test a hypothesis or no difference, what do you think I should do? The difference. So there you go. I calculate the difference here. Then we don't like negative numbers in statistics. Negative numbers doesn't mean anything to us. Negative numbers is a vector. I don't know if those are familiar with vectors, right? Vector going up, a vector going to the right, a vector going to the left, a vector going down. I mean, it's not plus or minus. It's a direction, right? It's where is going. It's a deviation above the expectation or is a deviation below the expectation, but the distance of those deviations is the same. It's one up or one down. That's why we have to eliminate the negative numbers. You can do this using absolute values or squaring the values depending on the scenario. When you calculate variances, we do the square. When you do the mean absolute deviation, remember the mean absolute deviation, MAD, that could be in your exam as well because that's level 1 material. The MAD, mean absolute deviation, we take all the deviations, remove the negative signs, add, right, and divide it by the number of observations. That's my MAD, M-A-D. So in statistics, deviations can be eliminated, the negative deviations can be eliminated by squaring it or doing the absolute value, okay? All right, the good thing about squaring is that in the end, you can unsquare, in quotation, take the square root, which is the standard deviation, okay? So when I'm able to do something and then in the end, I can bring it, let's say, imagine this, I'm taking the numbers to a second dimension when I do square. Well, in the end, I have to bring back to reality. That's more or less. So that's why squaring, it's very used in statistics because I can do the opposite, to reverse what I did. When we do the absolute values, we don't have that option to undo, right? So, but then the idea here is thinking about distance, right? One up, one down, one left, one right, but just like in absolute terms. All right, now I'm going to have here the absolute difference. When I have the absolute differences, then I will rank. Look at that. Rank. That's the key word for non-parametric tests, right? The ranking. So rank the differences. So now I took all those differences here and I'm ranking. 1, 2, 3, 4. Okay. They repeat, get the same number, right? The same idea. All right. Now calculate the test statistics for the Wilcoxon sign ranking test. Is the sum of the ranking for the positive difference. So now I have to add the ranks to come up with a number. Okay, and now I'm going to make a conclusion. If the test statistic exceeds a critical value, there's always a critical value. Always. Okay, to compare, reject or not. Now, this critical value is not coming from a normal distribution table, t-distribution table. No, critical value, in this case, will be assigned, right? And you don't need to know how to get it because that will be definitely out of the scope of the exam, okay? So there you go. So if your ranking, the summation of the numbers in your rank is more higher than the critical value, then you're going to reject the hypothesis as we always do, okay? All right. Look, I prepared something for you. So that's called the Wilcoxon rank test. So question is, when do I use the Spearman test? When do I use the Wilcoxon test? I know they're non-parametric tests. What are the similarities? When do I use it? What are the characteristics? What is all those elements of those two? Thinking about that, I said, you know what? You might get a question. Right? You might get a question in the exam that you're gonna have to do it, answer some questions related to those tests. So because of that, okay, I created here a little table for you. I'm gonna show in a second, very soon. Okay. There we go. It's coming. There we go. Too much. Let's see if I can put this whole table for you in one, so you can see the whole table in the image here. Okay, I'll let it go. And if you can't, then this one, you have to get it in the book. Yeah, we're not going to be able to see this whole thing. Let me try one more time here, just in case. Yeah, it's not good. So let's make it more visible and then go one by one. Okay, so be it. If you like to take a picture, okay, what I'm going to show you now, then I will pause for you. There we go. Let's do this. That's good size. Okay. So what I put here, friends, is the key points for the Spearman and the Wilcoxon test. Okay, Spearman is for correlation. Wilcoxon is for performance, for comparison, for independence. Okay, so look at the purpose. Important to know the purpose of each one. Now, which type of data we use? Okay, ordinal, interval, ratio data, meaning just like regular data. You're gonna ordinal means you have to rank the data. Assumptions: no normality or linearity. Okay, no requirements for equal variances. Right. No assumptions on normality, independent samples. So those are the assumptions of those methods. Okay, which approach? How do you do it? Okay, what is the interpretation of the results? If it's correlation, goes from -1 to 1. Okay, the Wilcoxon, right, was going to compare the median of the two groups. The p-value indicated distributions are different. Okay, or if the critical value it's lower than the t-test, then you're going to reject that hypothesis, right? When you're going to use them, okay, the pros and cons, right there, pros and cons. It's important. Pros and cons could be questions in exam. I always like questions of pros and cons, right? Which of the one most likely is, which one of the ones is least likely is, right? Or negatives and positives. Anyway, so imagine the questions about pros and cons could be in the exam. And when to use it here, an example, assessing the relationship, correlation, and comparing returns. Look at that, okay? So let's say John, CFA, financial analyst, is looking for a non-parametric test for correlation of two variables. Which one would John prefer? Spearman rank, Wilcoxon rank, chi-square, see what I'm saying? Questions don't have to be too difficult. Ooh. They don't have to be too difficult, people. Okay, they could be just a question of definition, a question of pros and cons. Anyway, okay, all right. I think that's good enough, right? Let's conclude. Let's just go back there and see if I'm missing anything. No. Yeah. The next one. So let's do the usual. Let's go over the key points and we can finish the video, right? Explain the hypothesis test of population correlation coefficient equals 0. So I already did that twice, actually, this video and the previous one. Determine whether the hypothesis is rejected for a given level of significance. We already know how to do that, I hope. Right? If your calculation is higher than the critical, reject. Explain the test of independence based on contingent table. Okay, we already did that. Okay, that's actually a good learning outcome for you to review. All right, test concerning correlation, parametrics and non-parametrics, check. And then the test of independence using the tables. I think we did all here. So I'm satisfied with the way this video went. Okay, there you go, friends. So that concludes the parametric, non-parametric test, the learning module. Next learning module, very important, is linear regression. So linear regression, it's, let me rephrase that. It is important, yes. Should you expect a lot of questions on level 1 linear regression? Not many. Linear regression level 1 is just a simple regression. So simple regression, there's not much to ask about it. Multiple regression, level 2, then we're going to have more questions to ask. Therefore, linear regression, the same advice, linear regression, which is the next video, same advice that I gave before. Focus, do a good job understanding to make your life easier for level 2. Okay, but not necessarily there's going to be a super heavy component on level 1, because I don't believe you will. Right? There's more things to ask on level 1. They have rates of return, decision trees. There's so many others, right? That linear regression, it will appear in the exam. Yes, I think that's high chances, but not too many questions. And I don't think it's going to be too complicated questions. It's going to be questions related to assumptions, definitions, and etc. All right? That's it, friends. I am done. I will see you on the next one. Bye-bye.